Hey, good morning, everybody. Sorry yesterday's video was so late. We'll try to get this one a little bit more on time today. Today, we are going to continue to look at contextual applications of differentiation. And today is local linearization. Local meaning nearby, linearization meaning make it a straight line. The students will be able to approximate values using local linearization. I need to introduce a little bit of vocabulary to you. It's not actually new. A new word to you, but it is new in calculus. So we have the term concave up, which is the one on the left. It means that your concavity can kind of hold a cup of water. It doesn't have to be that whole piece. It could be just half of that upward parabola or half like this. All of those are concave up. We also have concave down, which means that it wouldn't hold water. And again, it could be half of the parabola on either side. So concave up and concave down. The tangent line of the function at x equals a can give you an approximate value of f of x for points close to x equals a. And so that's the key word right there, is close. It doesn't work for values that are far away, but only those that are close. So overestimation versus underestimation. If a tangent line is drawn below the curve, it results in an underestimation. However, if the tangent line is drawn above, let's make that one above the curve, it results in an overestimation. Now, what does that look like? I'm kind of a picture person here. So to the first one, if we draw below the curve, so here's my curve, here's my tangent line, and if I'm checking out the value over here, my tangent line is below the actual curve. So the line would be the approximation and the curve would be the actual. Your approximation becomes an underestimate. And the one over here, oh, did I put that in the middle of my picture? I'm not sure. There we go. And the other one, if I have a tangent line drawn below the curve, above the curve. See, I didn't even look at my own typo. So here is my curve, tangent line is above. So if the tangent line is the approximation and the curve is the actual, now my tangent line results in an over approximation or overestimation. Okay. What does this look like for you? I'm going to zoom in here a little bit. Given the function f of x equals 5x minus 2x cubed minus 2, estimate f prime of 1.1 using the tangent line at x equals 1. Well, the good news is tangent lines. We know how to do that. I want to show you what this graph looks like. So I graphed this already for us in Desmos. This idea of linear approximation. If you zoom in close enough, any curve becomes a straight line. So here is the point 1, 1. It's going to mark the maximum. That's okay. So this curve was 1 over here. It doesn't want me to mark that, but that's okay. You know what? Let's do this. Can I say x equals 1? Will it graph a vertical line? Yes, it will. That's how Desmos is awesome. All right. So we have the point 1, 1 where x equals 1. So I just want to zoom in a little bit. Focus on that red curve, not the blue one. If you zoom in far enough, any curve looks like a straight line. And that's the point here, is we're using that idea of a straight line linear approximation. Now, if I go back to a normal viewing window, I know that it's not a straight line. However, if you get close enough, it acts like a straight line. So that's what we're looking at. We're looking at estimating it with a straight line. So the good news is you know how to find the equation of a tangent line. And remember that we're starting with that point slope idea. So I've got f of x. Oh, I'm going to pause and restart because there's some lag here. All right, so f of x, helps if you're not on the eraser, f of x minus f of a is equal to f prime of a times x minus a. This, if you recall, is point slope. Now, it's the same thing as, and I'm just going to remind you of this, y minus y1 equals m times x minus x1. I just want to show you that this is what you already know. But we took the version with the function notation and we rearranged it a little bit. We said f of x is equal to f prime of a times x minus a plus f of a. Now, I did a little learning over the weekend and I learned that this is called the Taylor form. That it was this kind of hybrid form between point slope and slope intercept. Turns out has a name. It's a Taylor form, and that's going to be important to us later on, but not right now. Don't worry about that. But this is the version of the equation of the line that we are going to complete. So what do we need to know? Well, we need to know f prime of a. Well, f prime is the derivative, so let's figure that out. F prime of x is 5 minus 6x squared, and the derivative of 2 is 0. But we're evaluating this at 1, so that's a pretty handy answer. This is 5. Oops, I want that to be 1. 5 minus 6 times 1 squared, so 5 minus 6 is a negative 1. So that's good news. We have the slope. The other thing we need to know is f of a. Now, from our graph, you can probably figure out what that is already. It was 1 if you don't remember, but I'll just show you. So f of 1 is 5 times 1 minus 2 times 1 cubed minus 2. So 5 minus 2 is 3. 3 minus 2 is 1. So f of 1 is 1. So we have the ordered pair, 1, 1, 1, and we know our slope is negative 1. Now, let me see if I can shrink all this so we can still do some work here. Hey, look at that. It's a little teeny tiny, but if you need to go back, you can. So we know that we have f of x equal to f prime of a, which we said was negative 1, times x minus 1 plus 1. So remember, this is the equation in the tangent line. This is our Taylor form, which is kind of like the point slope form. So we're going to estimate f of 1.1 using the tangent line approximation. So all that means is I replace the x's with 1.1. So f of 1.1 is equal to negative 1 times 1.1 minus 1 plus 1. Now, if you notice, I didn't pick up my calculator once for this. You should be able to do this without your calculator. Negative 0.1 plus 1 gives us 0.9 rather. There we go. So there is my approximation for 1.1. Now, I want to show you on the graph again. To me, it helps to see what's going on. So there's our x equals 1. 1.2 is over here. 1.1. You know what? Let me put another graph in there. So the green line is 1.1. Now, in actuality, it hits the curve at 0.8, but we said our estimate was 0.9. So remember, it's an estimate. It's not perfect. And we said it was y equals negative 1, x minus 1, plus 1. All right, there's a lot going on here. Let me turn this one off. There we go. So if I zoom in over here, 1 is where we set up the tangent line. Actually, I guess I need to turn that back on. So here's the tangent line, and the purple is the tangent line. And then we wanted to find the approximation at 1.1, which is the green line. So if you look at these two values, the red curve is the actual curve, but the purple tangent line is the approximation. So yeah, they're close. It's not exact, but they're close. So if I kind of zoom out and look at the whole picture, yeah, it's a pretty good approximation. All right, let's hop back into our notes. Part B. And it looks like I need to pause this again. For part B, would this be an over or under estimate? Well, on the other page, if you recall, we had the curve. We said the tangent line was here. This was 1, and we were over here at 1.1. Well, from the picture, we know it's an overestimate. But if I can't use my calculator and I can't graph this, how do I know? Well, you got to know if it's concave up or concave down. And concavity actually comes from the second derivative. Concavity comes from the second derivative. We'll do more of that later. But the first derivative we had said, I'm going to graph that from my teeny tiny work, is 5 minus 6x squared. The second derivative is a negative 12x. So we want to test it at 1. So the second derivative at 1 is negative 12 times 1, which is negative 12. Now, if it's a negative value, this is concave down. If it's concave down, the tangent line was drawn above, and my tangent line would have an overestimation or an overapproximation. So because it's concave down, the tangent line is above the curve, so the tangent line has an overestimation. Okay. Example 2, consider the differential equation, and I don't think we've used that expression before, but a differential equation is just, hey, here's the derivative. E to the y equals 2x squared minus 5x. Let y equals f of x be the particular solution to the differential equation with the initial condition f of 2 equals 0. What? What's all of that? It's very mouthy, very wordy. F of 2 equals 0. I've had this discussion with a few students, but just a reminder, all this really is the ordered pair. It's 2 comma 0. That's all it means. So if you are more of an algebra person, and remember I teach algebra at the same time, so I go algebra brain sometimes, that it is the ordered pair 2 comma 0. Write an equation for the line tangent to the graph of f at the point 2, 0. So remember, we want to fill in that equational line. I'm going to go with that Taylor form again. Truthfully, it doesn't matter. If you're on the AP exam, you can use the point slope form. We teach slope intercept form in Algebra 1, but point slope form is actually more helpful in further math classes, and then we get to this Taylor form. The nice thing about this problem is they gave us all the information that we need to know. So we have 2, 0. So just if we need to write it out, a is equal to 2, and f of a is equal to 0. If it makes more sense to have it in that notation, we can definitely do that. So f of x is going to be f prime of a. Let's come back to that in a minute. X minus a, so x minus 2 plus 0 on the end. Now, f prime of a is the slope. They gave us the derivative, so that's really handy. Let's switch colors here. So f prime of a, let's do this over here, is the derivative. Now, this notation doesn't work out perfectly because this is not necessarily a function the way that it's written. But let's use, yeah, that's okay. Let's keep going. So this is e to the y, and the y value is 0, so e to the 0. 2 times 2 squared minus 5 times 2. All right, e to the 0, anything to the 0 power is 1, so that's kind of handy. Don't panic about the e. 2 squared is 4, 2 times 4 is 8, minus 10, this is a negative 2. So my slope is negative 2. So we have the equation of the tangent line. F of x equals negative 2 times x minus 2. You don't really need the 0 at the end. Got it. Write the equation for the tangent line. Use the tangent line to approximate f of 2.2. So in this particular problem, we don't actually have the original equation. We don't know what kind of curve it is, but we have the derivative. We have the differential equation. So f of 2.2 is going to be negative 2, 2.2 minus 2, This is a -2 times 0.2, which is a -0.4. Awesome. Awesome, awesome. So tangent lines, nothing new. You've been doing tangent lines since Algebra 1. You've been doing tangent lines. Well, you've been doing lines since Algebra 1. You've been doing tangent lines since the first week of calculus. So not a bad lesson at all. Remember to work on all the practice problems. Tomorrow we'll ask you how much you completed, but reach out if you have questions. If you're in class, you can ask Mrs. Oakes. You can send me emails. I know several of you send me emails each day. That's great. Keep it up. Set up Zoom meetings if we need to. So keep up the good work. You really are doing a good job.